minutes? Okay, 45.
Okay, you tell us when you're ready for us to get off of here, Rich.
He sounds like he's kind of busy.
Yeah.
Euphoric.
All right.
Yeah.
All right. Hello, everyone.
Hello.
Hi there.
All right. I can hear everyone. John, we don't see you.
We don't see you. We don't hear you.
Sorry,
he
a little
is.
late. Whoops.
Here he is. All right.
Now we just need your smiling face, and we'll be
It's-
set.
It says I can't start my video because the host has stopped it.
Now
So
you should be able to.
The
There we
host is
go.
still sharing his screen.
Yeah, that's going to stop in a second here. There we go.
Okay. So how is everybody doing?
I'm doing fine.
Doing good.
Good. Well, we are up here at the
okay.
Chabot Space and Science Center. We're all gathered. Well, three of us are gathered inside the observatory that houses our 36-inch reflecting telescope called Nellie. And if you look at Rick Taft's image there, you see that
Head out of the way.
Nellie's up, but the roof is closed. That's
Here,
because
I can show you Rick Taft now.
all right. So unfortunately, the humidity tonight is a little too high for us to operate Nellie. So we're going to have to do a presentation about Saturn without actually looking through the telescope tonight. But we've got lots of good stuff to show you here, including some images taken recently of Saturn from Berkeley and some images taken of Saturn a couple of years ago using Nellie. So you'll see what it looks like in Nellie if we were to do a live stream. And also, we're going to talk a little bit about Saturn, why this particular date or this time of the year in Saturn's lifetime is important, and give you some close-up views of Saturn as well. So,
Well, before we get started, I have a PSA.
okay.
All right. So first,
And now a word from our sponsor.
now a word from our sponsor. First, I didn't introduce all of you. And so we have Rick Taft. There he is. Gerald McKeegan.
That's you.
and John Curry. And I'm Rich Ozer. And it's nice to be here again. I want to encourage everyone, especially if you're on Facebook, to look for that donate button at the bottom of your screen. Chabot relies on donations and public support, and today is no exception that we're asking for donations and for your participation in our wonderful future here. And we are much more open than the last time we did this, and we want to encourage the public to come up on Friday and Saturday nights to enjoy our telescopes live. But please contribute and help us out. If you're on YouTube, visit our website at chabotspace.org, and there's all kinds of information about becoming a member of Chabot or making a donation, and we truly appreciate it. So that's the end of my PSA.
All right. Well, Saturn is in the sky once again. Happens about once a year that Saturn reappears in our night sky. And the last few weeks, we've been looking at Saturn late at night with our telescopes here at Chabot Space and Science Center when we're doing public viewing. But we wanted to do a live stream presentation tonight because this past weekend, Saturn was at opposition. So I thought we'd spend a little time just talking about what we mean by opposition and why that's important. And then maybe just show a few images of Saturn and answer some questions about it. So if you guys are okay with that, I can get started here.
Sounds great.
I'm not opposed to it at all.
All right. Well, let's start out with what the heck is opposition mean? Okay. So you all know, hopefully, that the Earth takes about 1 year to orbit around the sun. Saturn, on the other hand, because it's much farther away from the sun, takes nearly 30 years to orbit around the sun. So every year, as the Earth makes its orbit, makes one complete orbit, Saturn will have moved only 1/30th of its orbit. And when we say opposition, that is the point where the Sun, the Earth, and Saturn are all on one line. And when we are at that point, Saturn is technically it's the brightest. And when we look at Saturn, we don't see any shadows on the rings of Saturn. So this is a good time to start viewing. Prior to opposition, Saturn tends to be in the night sky, but you have to stay up pretty late to see it. But after opposition, Saturn gets higher and higher each night. And so you can see it earlier and earlier in the evening. So if you're outside right now and you happen to have clear skies, you can actually see Saturn. Right now it's in the southeastern sky. It's one of the brighter objects up there. And unfortunately, we can't point our telescope at it, but it's there. And we have been looking at it, like I say, in the past couple of weeks when we had clear, dry nights. So this is what we mean by opposition. Got a couple of other images that I think I might share with you. This is an image of Saturn taken with our telescope, Nellie, our 36-inch reflector. This was not taken tonight, however. This was taken a year ago when we were at opposition back then. Opposition a year ago happened a little bit earlier in the year, and we happened to have a clear night. We could get an image. Actually, this was taken, I believe, a little bit past opposition, because one of the interesting things, and we'll talk about this a little bit more, if you look right here, I'm hoping you can see my cursor. If you look right here, you can just barely make out the shadow of Saturn on the ring. And this is what happens when Saturn is not precisely at opposition. We will see a little bit of a shadow on the ring. And so if we were to look at it tonight, we probably would not see a shadow. And that's one of the cool things about looking at Saturn at opposition is you don't get any shadows on the rings. There's also an effect called the Seeliger effect that causes the rings to appear slightly brighter when it's right at opposition. It's a little bit of a technical idea, but basically the ring particles, because of their orientation with the sun directly behind us, if you will, it makes the ring particles reflect a little bit more light than they normally do. And so they look a little bit brighter right at opposition, and that's called the Seeliger effect. Got some more images to show. Oops, don't want to show that one. There we go.
It has rings.
Yeah. This is an image that was taken a couple of nights ago. What was it? Sunday night, I believe it was. Is that right,
Yep.
Rick? Yep. Sunday night by one of our members of our local astronomy club, the East Bay Astronomical Society, and he was in Berkeley, and he took this image of Saturn with his amateur telescope. Now, the reason it's so clear is because he used an imaging process that's kind of interesting. And I'm going to let Rick kind of jump in here and explain a little bit about how he was able to capture this really sharp, clear image of Saturn.
The image that Gerald's describing, it was obtained from Bob Miner. And Bob is a member of the East Bay Astronomical Society and also Mount Diablo Astronomical Society. The image itself consisted of over 10,000 separate images. Each one of the images was 10 milliseconds long. And as Gerald mentioned, the images were imported into a software program where the best 50% or 5,000 images were processed to create the image you're seeing on your screen now.
So the way he's able to take so many images that are so short is he puts his camera in video mode.
Oh, well, yeah. He's actually
Yeah.
not using a DSLR. We normally use a DSLR
Right.
on Nellie, but Bob was using a special astronomical camera that records very short
Yeah.
frame videos. And that's how he's able to
Yeah.
do it. The frame rates are amazing, somewhere maybe in the 150 to 160 frames per second. And you need that really fast frame rate to freeze the effect of atmospheric turbulence. And the software program called AutoStacker is able to choose the best frames out of that large number and then later create this image.
And for those who are out there who want to try this technique, you can do it with a DSLR. You can do it with a Canon or Nikon camera that has video on it. And AutoStacker, which is the software that Rick just mentioned, is free. So you can download that and process the frames from your video. So for those of you interested in astrophotography, those are the two main components of trying this out.
Yeah. Now, the thing I want to point out in this image, since it was taken, I think, the day after opposition, you don't see shadows on either side of Saturn. There are no shadows on the rings. And you really can't tell, but the rings are a little bit brighter than they would be if, he took it a couple of weeks before or a couple of weeks after opposition. So this is a really great image taken from Berkeley.
So, oh my gosh!
Yeah, in the middle of all that light pollution and all that air pollution.
They have a better view of Saturn than we do in Berkeley.
And keep in mind this was taken with an 8-inch reflecting telescope, and a lot of skill there. So kudos go to Bob for a really great image there.
Yeah, that's really great. So. I wanted to share a couple of other images here. Let me see if I can find my way around to them. Oh yeah, this is the one I wanted to share. You're all aware that Saturn orbits around the sun every 30 years, and you notice in Bob's image that the Saturn is sort of tipped a little bit. It's tipped toward us so that the rings are easy to view, but that's not always the case. And this is a composite of several images taken by the Hubble Space Telescope that show us what's going on. Saturn's poles are tipped about 26.5 degrees relative to its orbital path around the sun. And it's always tipped and pointed in the same direction. So as Saturn orbits around the sun, the angle of the rings changes as viewed from Earth. And that change happens over a period of 30 years. And in 30 years' time, it goes from maximum tilt in one direction to maximum tilt in the opposite direction. And when it reaches the point where the rings are edge on, they in effect disappear. You might see a thin line, but you don't see the rings at all. Now, we're several years beyond the last time that happened, but that will happen again in a few years as the rings are now tipping back towards that edge-on point. And I think it's in 3 years that we will see the rings again edge-on. So it takes 30 years to go through a complete cycle from tilted maximum in one direction, then down to tilted in the maximum in the opposite direction, and then back again. That whole cycle takes about 30 years. And it's really cool to watch this year after year after year, because we can see Saturn every year. So year after year, we see Saturn tilting a little bit more. And eventually we see it edge on, and it's amazing to see all of a sudden the rings of Saturn just disappear. So that's again, these are Hubble images taken. These were all taken when Saturn was at opposition at different years. This is a close-up view of Saturn taken by the Cassini spacecraft the Cassini spacecraft arrived at Saturn in 2004, and it went into orbit around Saturn, and it stayed in orbit for quite a while. It eventually ended its mission in the year 2015. So for 11 years, Cassini orbited around Saturn, orbited in different directions, and got some spectacular imagery and a lot of science data about Saturn. And largely because of the Cassini mission, we now know that Saturn has 82 moons orbiting around it. And you see 4 of them in this image here. So there's one here, one there, and one there. When we look with our telescope here, Nellie, we can see sometimes 5 and occasionally 6 moons, but most of the moons are pretty small, and a lot of them are actually embedded in the rings. So we're not able to see them with Nellie, but we see the bigger ones, the ones that are easier to see. This was the Cassini mission, and I'm going to stop my share for a second here. If you guys want to chat about something else for just a second, I'm going to be changing my view here.
Well, and the other notable part of the Cassini mission was the probe that actually penetrated the atmosphere of Titan and discovered methane lakes.
Yep.
And
that was the Huygens probe.
The Huygens probe, and I hear that lakefront property there is very inexpensive.
Yeah. Getting there to buy it is another story.
Yeah, the largest moon of Titan, or the largest moon of Saturn, is called Titan. Titan has an atmosphere. It's a very cold atmosphere, so it's composed of large quantities of methane and ethane. And it's actually possible for methane and ethane to condense because it's so cold and rain on the surface of Titan. And because of that, when we get close-up views of Titan, we see what looks like lakes and rivers and streams, but they're not lakes, rivers, and streams of water. They're lakes, rivers, and streams of liquid methane. It's a really fascinating place. And as Richard said, the Huygens probe landed there back in 2004 and actually sent back some imagery. The images that they sent back looked like it had landed in a field of small rocks, except those rocks were not rocks, they were water rocks. Water freezes at that very cold temperature that's on Titan. It freezes so much that it's literally as hard as a rock. So there were what looked like boulders in the image, and those were ice rocks, not silica rocks or anything like that. So
water and methane, what more can you need?
Yeah, really. So I'm going to share some Cassini images here. So bear with me.
Is that methane on the rocks?
So let me ask you a question, Gerald. So you mentioned how how many of those 82 moons are embedded in the rings, and we're looking at this big gap there in the rings, about half an inch in from the edge.
Right.
Is that caused by one of Saturn's moons?
Yes, it is. It's caused by the moon Mimas. The moon Mimas orbits a little bit outside of the rings, but there's a curious effect when you get into orbital mechanics. It's called mean motion resonance. And as it turns out, this part right here, it's called a Cassini division. Any object orbiting there would be in a 2-to-1 mean motion resonance with Mimas. So for every one orbit of Mimas, an object in this distance from Saturn would orbit 2 times around Saturn. And when you get mean motion resonances, it can cause problems for one or the other object. And in this case, because Mimas is the bigger object, it actually tugs on the ice particles in the rings. For those of you who don't know, the rings are composed mostly of ice particles. And Mimas will tug on those ice particles and try to pull them out of that 2-to-1 mean motion resonance. And that's what creates the gap. Now, there are actually a lot of other gaps in the rings of Saturn, and I'm going to show you a couple of them here in a few minutes. But this is an image from Cassini. When Cassini was orbiting in the polar type orbit, it changed its inclination at various times as it was orbiting around Saturn. So this was when it was in a high angle orbit, and a great view of Saturn from the side. So you can tell that the sun is to the left, and you can see the shadow of Saturn cast across the ring plane. That ring plane is actually very thin, by the way. It's only about 10 to 20 meters thick in most places. And you can see the rings. Now, when we take pictures of the rings from the Earth, it looks like there's maybe 4 or 5 rings. But when Cassini got close up, we came to realize that there are actually hundreds, if not thousands, of rings. And so I've got some more imagery here that I'm going to show you. This is a closer view of the rings. And now you can start to see how those broad rings that we see from Earth are actually composed of a bunch of thinner, narrower rings, almost like ribbons wrapped around Saturn. And in fact, the Cassini division does have some ring particles in it. It's just that most of them have been pulled to one side or another. You see here a couple of very small moons of Saturn. Saturn's moons, most of them are only a couple of kilometers across. So they're too small to be seen from the Earth. And that's why we needed a spacecraft orbiting around Saturn to discover them. Let's see, I'm going to go next image here. Here's a lower angle image. And once again, you can see how the rings are actually composed of thousands of rings. The issue here is that a particle orbiting around Saturn, the speed at which it orbits depends on how far away it is from Saturn. So ring particles that are in close to Saturn, like these, orbit much faster than ring particles that are farther away out here. And so you can't have a continuous sheet of ring particles. They have to sort of self-separate into different little rings that orbit at different velocities. Next,
so it's interesting to note that for a long time after Saturn's rings were discovered, the common belief was that they were solid.
Yes. Yeah.
Like a phonograph record.
Yeah. Yeah. The first one to see the rings of Saturn was Galileo back in 1610, using a very small, crude telescope that he had. But he was able to make out something around Saturn. And in his notebook, he sketched them like they were 2 little handles, like teacup handles on the side of Saturn. It wasn't until a few years later that some other astronomers using better telescopes were able to recognize them as rings. But as far back as the 1600s, astronomers knew that Saturn had rings around them. They weren't quite sure what they were, and for a long time, they actually believed that they were solid sheets of some kind. So this image is an animation taken by combining a bunch of separate images, and it shows a little moon within the ring structure. And what you see is the gravitational disturbance of the ring structure by that little moon. So the ring structure, the rings itself are very thin, a bunch of mostly small icy particles. And I think I mentioned already, the ring's thickness is only a few meters, 10 to 20 meters thick in most places. But what happens is when you get a little moon embedded in the ring like this, that moon has some gravity, and the gravity wants to tug on the ring particles and disrupt their orbits. And so what you see is the ring particles being disrupted out of the ring itself and kind of pitched up or pitched down a little bit by the gravity of that little moonlet. Now, what you notice is the ring particles closer to Saturn are kind of in leading the moonlet, and the ring particles farther away are trailing it. That's because of this differential in orbital velocity. The ring particles closer to Saturn are orbiting a little bit faster than the moonlet, and the ring particles farther away from Saturn than the moonlet are orbiting a little slower than the moonlet. That's why you have these disturbances going in opposite direction depending on which side of the gap that moon has created within the ring. So really interesting to view this. And again, we owe this all to Saturn, or to the Cassini mission, which really taught us a lot about Saturn.
Well, we owe it to Saturn also.
And now this is something that I just think is amazing. This is the ring plane crossing by Cassini. So what happened was the Cassini spacecraft was in a polar orbit, and they captured a whole series of images of the same part of the ring structure so that you could see what it was like as it crossed the ring plane going from north to south. Actually, I think it was going from south to north. And so you can see the rings. You can see some moons drifting by every once in a while. I'll run that again here. So here are the rings. Here's the Cassini division. This is called the Encke division. And every once in a while, you'll see a moon go by. There's one right there. Should have another one. There's one right there going by. And then there was one that'll come by in the background. And this really gives you a sense of how thin that those rings are. They're just not very thick at all. And that's because they're orbiting basically above the equator of Saturn. So they are on, orbiting in the same direction that Saturn is rotating. And you get those very thin rings because of the gravitational perturbances that keep everything within this very thin plane. So that's a Cassini tour of Saturn.
No, it was pretty interesting, Gerald. I mean, when the spacecraft transited over the poles, I guess the rings almost disappeared for a second, just really underscoring how thin they are. One of our viewers, Brandon, had asked, will the rings be around forever, or will they dissipate slowly or be absorbed into the planet?
Yeah, we actually think the rings will eventually dissipate. There's a number of forces that are slowly tugging on them. We talked about how Mimas is tugging on them. The rings, are made out of ice. Eventually that ice will sublimate away. So we do believe that, hundreds of thousands or maybe a couple million years from now, the rings will slowly dissipate. But one of the interesting things is we always talk about Saturn and Saturn's rings. And we tend to think of Saturn as being the only planet in our solar system with rings, but that's not true. In fact, all 4 of our gas giant planets in the solar system have rings. Saturn has the most prominent rings, the easiest ones to see, especially if you're looking from Earth. But Jupiter, Uranus, and Neptune all have rings. They're just not as prominent as Saturn's rings. It's possible that one time they were, but they are no longer very prominent. So you have to have a better way of viewing them. And we just recently got a whole new way of viewing the rings of some of the other planets. And I think Rich is about ready to share a really interesting view.
I am. Thanks for that, Gerald. And I want to say that we had no idea that Jupiter had rings until the Voyager 1 spacecraft did a flyby, and everybody was astounded to see that Jupiter also had a rings. And we can't see it from ground-based telescopes. And the only way to see it was from a spacecraft. Now, very recently, we sent a very well-known spacecraft to a distant spot in the solar system, and it's the James Webb Space Telescope. And recently, they pointed it at Jupiter, and I want to show you this photo. This is a photo of Jupiter taken by the James Webb Telescope quite recently. And you notice that it looks kind of weird, right? Because it's photographing it in the infrared spectrum. The James Webb Telescope is an infrared camera, and there's a lot of reasons for that. I'm not going to get too much into that. But what you can see on each side is a very faint but quite obvious ring.
Right.
And there is a fair amount of speculation that this ring was thicker and more prominent in the past, but it was worn away gravitationally by Jupiter's moons. And I guess there's no reason to think that it's going to be any different with Saturn given enough time. So anyway, I wanted to share that.
This is actually a great image. It really shows how the red spot is a very warm spot on Jupiter.
Is that a ring?
Is that a moon? I think that may be one of the moons.
The moon shadow, I think.
I think it's a shadow. Yeah.
Oh, is it the shadow?
That's like a shadow to me.
That bright thing with the diffraction spikes on the left there, is that one of the moons, or?
I'm not certain.
Yeah, okay. I'm not sure what that is.
Okay.
But it looks like there's another shadow over on the left side down low.
Yeah, over here. Yeah, it's a really neat photograph.
Yeah. This is just really interesting, and it's just an example of all the new science we're going to be getting out of the James Webb Space Telescope. It's just, I'm really looking forward to all the stuff they're going to be able to see here.
Yeah.
Not only of planets in our own solar system, but planets in other solar systems, the composition of atmospheres of planets in other solar systems, looking backward, almost back to the Big Bang. We're just going to learn so much that we weren't able to see before because of dust and because we were looking in the visible part of the spectrum. And we're going to see a whole new universe with the James Webb Space Telescope. So stay tuned. There's a lot more to come from the James Webb Space Telescope.
Hey, Deborah asked a great question. She says Jupiter has moons in the ring too. I don't believe so. Yes. I don't think there's anything that close, is there?
Io might be.
Yeah, Io is pretty close. Io takes just under 2 days to orbit Jupiter, so it might be either within or very close to the ring. So.
Yeah, but when you see Io near the side of Jupiter as it's coming out from behind the planet, it goes quite a ways out. Way beyond.
I think you're right. Yeah. I think you're right. Yeah. I just realized I turned off my video.
Yeah, we lost you.
All right. Well, I can see some more questions coming up. Anything here that we haven't answered already?
Yeah, it's probably a good time to break for questions here. I was trying to look up the size of the ring versus Io's orbit, and I've been unsuccessful.
We've got a couple other things to show you, but we want to make sure we get all the Saturn and Jupiter questions taken care of before we move on. And if there aren't any, we can certainly move on to some other objects that are in the sky tonight that we can take a few minutes to talk about.
Okay.
Yeah.
Scrolling through here, seeing what I can find.
Somebody asked, will you tell us a bit about the hexagonal cloud? Yeah. So if we had a polar view of Saturn that was in sunlight, I don't have one.
I can bring one up here in a sec.
Yeah. If we do that, we should be able to see what looks like a hexagon-shaped cloud at the pole of Saturn. A hexagon is a six-sided polygon. A stop sign is a hexagon. And there is a hex. Huh? Is it?
It's an octagon.
Octagon. Oh, yeah. You're right. Oh, there we go. All right.
There it is.
Okay. Yeah. So this is not a stop sign. You got me.
And it's not red either.
So anyway, this is the hexagon at Saturn's pole. And because of Saturn's rapid rotation, Saturn's day is only 10.5 hours long. So you've got a planet that's 9.5 times wider than the Earth, and its day is less than half as long as the Earth's day. So it rotates very rapidly. That causes the gas. Saturn is a gas giant, so the gases orbit or rotate around the planet very rapidly, and they rotate at different velocities at different levels or latitudes. And what we see near the poles is because of that rotation and because of the variation in rotation, it produces this hexagon effect. Now, we're still not 100% sure why it does it as a hexagon rather than a nice circle, but it does it, and this has been verified numerous times. So really interesting effect here, and it's just because of the circulation of the clouds and the differential circulation of the clouds as you go to different latitudes within the atmosphere of Saturn.
We have another interesting question. Why are the rings different colors? And I don't know that they're really different colors, are they? Isn't it?
Yeah, they are.
A shade?
They are a little. Yeah, there's different shades of color. Some tend to be a little more brown than others. Of course, when we see them from Earth, because we're looking at so much bright reflected sunlight, we tend to see them more as white or yellowish in color. But when you get up close to them, they have shades of tan and brown. And we're not sure precisely why there's, different rings seem to be obvious different shades of brown. It's likely that they're because of the composition of whatever the icy body was that broke up to form those rings in the first place. One of the theories for the rings is that it was a icy moon that got close enough to Saturn to where Saturn's gravity actually tore it apart. And that's what produced the rings. We know one of the rings is actually not from a moon that broke up, but rather from a moon that's ejecting ice. One of my earlier images showed kind of the outer portion of the rings, and you saw a very thin ring at the farthest distance from Saturn. That's called the E ring. And the E ring is actually produced by ice particles being ejected by the moon Enceladus. Enceladus is an icy moon, possibly with a liquid water ocean under the ice. And there are fissures in the ice, and water is ejected up through those fissures. And as soon as it hits the vacuum of space, it freezes into kind of a snow, which, because it's being ejected up through those fissures with enough force, it can actually escape the gravitational pull of Enceladus, and those icy particles go into orbit around Saturn and produce this very thin E ring. So, some of the rings are potentially from an icy moon that broke up, but some of them can be from ice being ejected by the moons of Saturn right now. So I wish I had. If I had thought of it, I would have brought. I've got an image actually showing Enceladus. It's a view from Cassini, and it's a little short movie where you can actually see what looks like ice geysers coming off of Enceladus and spewing ice crystals into the sky. And those crystals eventually drift off into the E ring of Saturn. All right. How are we doing on questions here? Can you show us how to find Saturn in the sky this week? Yeah, that might be a little bit of a challenge. If you guys want to chat for a second, I'll bring up Stellarium and maybe we can.
Yeah, I was about to suggest that. That's a good way to do it.
Yeah. Why don't you guys go ahead and I'll bring up Stellarium here and see what we can do here.
Yeah. Let's see what else we've got in questions in the meantime.
I do have Starry Night open right now, and if you can find the teapot, you can just look to the left of the teapot. It's in Capricornus, but just a little ways left of Sagittarius.
You say you've got Starry Night or Stellarium already up?
Not on my laptop, on my other computer, so I can't share it.
All right, so I'm bringing it up here.
Yeah.
There's some software that we use, and I would really recommend this to everybody. There's a software package called Stellarium. It's STELLARIUM. It's free software. It runs on your Windows laptop or desktop, and it's planetarium software. And if you set it up with your location and the right time of the day and the year and so forth, it will show you what's in the night sky at any given time during the course of the night and any given time during the year. You can actually, set it for different dates and times, set it for different locations and so on. It's a really handy piece of software for answering that very question that you're asking about. Where is Saturn? So Saturn right now is in a constellation Capricornus. I'm going to share a view of it here in just a second here, if I can get it set up.
So one thing you might do, Gerald, is point out the summer triangle. And if you draw a line from Vega through Altair, it sort of more or less points towards Saturn.
Yeah.
Well,
yeah.
The other thing that people can do, if you're not familiar with stars in the sky per se, Saturn rises at about 7 p.m. local time for us. And if you look towards the to the east southeast, at about 7 o'clock, you'll see what looks like a yellowish star.
You won't see anything because it'll still be too bright, Rick. You got to wait a little bit later than that.
Yeah.
Well, actually, yes, you're right. So about at 9 o'clock, it's still east southeast. At 9 o'clock, should be dark enough to see it.
Yes.
Okay.
There we go.
Here's Stellarium, really nice software. This is looking straight south right here. All right. So right now, Saturn is in the southwestern sky. It's low in the sky. There's three southeast. Thank you. There's three stars that John was talking about called the Summer Triangle. That's Altair, Vega, and Deneb right here.
That's Deneb.
And these three stars form what we call the Summer Triangle. And the long axis.
They are very bright, I want to mention too, because they'll be easiest to see as soon as it starts to get dark.
And then low in the sky, below the Summer Triangle, this is the constellation Capricornus. If you're anywhere in an urban area, you won't be able to see any of the stars in Capricornus. Yeah. But if you look right now at this time of night, if you're in the Bay Area or in California, look southeast and about 25, 30 degrees above the horizon, you will see the planet Saturn. It will be slightly yellowish when you look at it and brighter than most of the surrounding stars.
I'd like to also point out that if you look next to the red E,
just coming up.
Somebody else is peeking up over the horizon.
Yep. And next month, Jupiter will be joining Saturn in the sky, and in late October, Mars will be joining Jupiter and Saturn. So we're going to have all 3 planets in our night sky come October.
Yeah,
So
just look
really,
for that big red E on the horizon.
Yeah.
That's right. Yeah. Yeah, that's
And so anyway,
Just
again,
to
this is
visualize
a
that,
program called Stellarium. It's a great program. It's a lot of fun for just finding your way around. You can set it for different times. You can set it for different locations. You can set it so the clock runs fast, or the clock runs slow, or the clock stops. You can do all kinds of different things. So it's a great program to have, and I really recommend it to everyone. So they can, do their own navigation of the night sky. All right, I'm going to stop my share here.
Yeah, that was good. Thanks, Gerald.
Okay.
And by the way, that Stellarium program is also available for phones. They have an Android version, an iPhone version, and it's really a bargain. It's a really good.
Yeah, I always forget
software
about that because I don't have a smartphone.
Well, that's because you're smarter than your phone.
That's exactly right.
The rest of us need that crutch.
Gerald carries. Gerald, you carry around a dial phone, right?
Yeah,
almost. I have my
flip phone.
My little flip phone. There you go. That's all I need. And personally, I think they call them smartphones because they suck the smarts right out of your brain.
Yeah, I think so.
I think that's exactly right.
Yeah.
We got an interesting question. I'm not sure I understand the question completely. It says, is Enceladus like Europa, but Saturn orbiting? Well,
it's sort of. Yeah, sort of.
It's an icy moon
that may have liquid water.
Yeah, just like Europa. Yep. So it's sort of the same, but not quite. They're not the same size, and there are some other differences as well. But it turns out there are a number of moons around both Jupiter and Saturn, and possibly elsewhere, that are icy moons, or they're covered with a layer of ice that we think covers a liquid water ocean underneath. So interesting place. And, of course, the question is it possible that that liquid ocean might harbor life? Anyway, got a couple other things I wanted to show you here. We got about 15 minutes left. So if you'll bear with me here, I think we'll look at another object. Yes. All right. So there's other things in the sky besides the planets right now. And one of them that I wanted to point out to you is called the Ring Nebula. Now, a minute ago, we talked about the Summer Triangle. One of the stars in the Summer Triangle is called Vega. Vega is the brightest star in the constellation Lyra. And a really interesting object in the constellation Lyra is the Ring Nebula. The Ring Nebula is the remnant of a dying star. This is a star that was once like our sun, but it grew old. When it got old, it swelled up, became a red giant. As a red giant, it has some pretty turbulent atmosphere. There's a lot of convection going on. And because it's so big, its gravitational hold on its outer layers is not very strong. So that convection causes strong winds that actually blow the outer layers of gas on the star out into space. And this goes on for tens or hundreds of thousands of years. And slowly but surely, the star loses mass. And as it loses mass, it begins to expose the interior of the star. And so eventually the star loses half or more of its mass. And at the same time, it's running out of fuel at its core. So the fusion process, which is what generates the heat of a star, generates the star's energy, that fusion process, which happens at the core, it eventually runs out of fuel. And when that happens, what's ever left of the star collapses into what we call a white dwarf. The white dwarf is extremely small. The star may have been 1,000,000 miles in diameter when it was a young main sequence star, but the white dwarf is only about 10,000 miles in diameter. It's extremely dense, extremely hot, and it emits a lot of energy as ultraviolet radiation. And that ultraviolet radiation goes out and it hits all that gas that was being blown off for tens of thousands of years before it became a white dwarf, and ionizes the gas and causes it to glow. And so we see this glowing ring or shell of gas around the white dwarf, which you can barely make out at the center of the donut hole. And this is called a ring nebula. It's one of the most popular things for amateur astronomers to look at and photograph. Do you have a comment, Rich?
No, I'm sorry. Okay. We were looking at various questions.
Okay.
Yeah. Hold on.
There we go.
Question: how big a telescope is? Oh, go ahead.
I was just going to ask Gerald: is this image of the Ring Nebula from Nellie?
It is. This was taken with Nellie. It's a 30-second exposure with a digital SLR camera. It was actually done kind of as a demonstration one night when we were having our annual gala, which, by the way, is coming up in October. We had our annual gala, which is a big event, and a couple of folks came out here, including the mayor of Oakland, and they came out and were asking, well, how do you guys take pictures through the telescope? So we grabbed a camera, put it on the telescope, and took this 30-second exposure, and everybody got to see a very simple demonstration of how we take images with the telescope. And the night just happened to be a really good seeing night, so we got a nice image of the Ring Nebula in the process.
Sam asked how big a telescope is needed to see this.
Not very big at all.
Yeah. I've seen it with an 8-inch.
Yeah, I've seen it even smaller with a 4-inch telescope.
You have to qualify that though, because if you see the ring with a smaller telescope, you're not going to see this beautiful color. You're only going to get that color if you take an exposure with a color camera.
Yeah. And well, even if you're looking live through Nellie, you won't see that.
Correct, right?
Of color.
Unless you're a kid.
Right.
and speaking of kids, I mean, when they're looking live through Nellie, some describe it as a smoky Cheerio.
Yeah,
smoky Cheerio. Or a ghostly Cheerio, yeah.
Or a ghostly Fruit Loop, actually. Cheerios aren't blue. So, by the way, the colors that you see are indicative of the chemical composition of that cloud. That cloud is made mostly of hydrogen. Hydrogen glows when you hit it and ionize it with ultraviolet radiation. It glows in kind of a reddish, deep reddish color, so you can see that. But also in the cloud is a small percentage of oxygen. Oxygen, when it's ionized by ultraviolet radiation, glows in this really bright turquoise color. And so it makes it look like the cloud is mostly oxygen, but it's only because the oxygen glows so much brighter than the hydrogen does that we see it, and that seems to be the dominant color. But the actual dominant element in this cloud is hydrogen. And by the way, this donut is about 1 light year across. So our entire solar system would fit inside the donut hole. Okay, so one other thing I wanted to share with you, another interesting object that's in the sky tonight, is this guy right here. This is M13, the globular star cluster M13. It's about 25,000 light years away. By the way, the Ring Nebula is about 2,300 light years away. So with M13, we're talking 10 times farther away. A globular star cluster is like a ball of stars out in space. There are about 180 of these orbiting around our galaxy. The stars in the cluster are very close together. If you lived on a planet orbiting around one of these stars, you wouldn't have a nighttime because there would be so many stars so close to you that would just light up your night sky. The stars orbit around the center of the cluster in highly elliptical orbits. So they go in close to the center. When they're close to the center, they're moving very fast, and then they swing way out. And as they go out farther from the center, they slow down, and eventually they turn around and they come back in. And so they're going through these very elliptical orbits, fast when it's close in and slow when it's far out. Like I say, there's about 180 of these out there, and these are all very old stars. These are among the first stars to have formed when our galaxy was forming. So they're all more than 10 billion years old. And M13 is one of the easiest to find. It's in the constellation Hercules, and it's a great target for even small telescopes. You can spot M13 if you know right where to look. There's a star pattern in Hercules we call the trapezium, and M13 is on one edge of the trapezium. I'm sorry, not the trapezium, the keystone. Thank you. I'm getting
your trapezoids mixed up.
My trapezoids mixed up.
your asterisms.
So it's called a keystone. It's called a keystone, which is shaped like a trapezoid. It's 4 stars in a trapezoid shape, and you'll find M13 on one edge of the trapezoid that we call the keystone.
Hey, we have a question from a 4th grader. I think the name is Sarab. I'm not sure exactly the pronunciation, but she wants to know how many nebulas have astronomers found so far.
Oh gosh,
it's got to be a very big number, but
yes,
I don't have any idea
hundreds
what
of them. There are different kinds of nebulas. The word nebula means cloud. So there are different kinds of clouds out in space. Some of those clouds are the remnant of dying stars, like the Ring Nebula that you saw. The general category that we use for that type of a nebula is a planetary nebula. It has nothing to do with planets, but a long time ago when astronomers first saw them, they thought they were planets in the formation process. Turns out they're stars in the at the end of their lives, but the name planetary nebula stuck. So we still use it to describe these things. And just talking about a planetary nebula, there are hundreds of them in the sky that we can see. We even see them inside of the globular clusters. And then there are other nebulas, which are clouds of gas and dust that are condensing and forming new stars. So a cloud can be the remnant of a star that's dying, a star that dies in the slow process to form a planetary nebula, or a star that dies in a supernova explosion. Those will create these certain kind of clouds. And then there are other clouds out there that are clouds that are condensing and forming new stars. Some clouds emit a lot of light. Some clouds reflect a lot of light. So there's all kinds of different nebulae out there, and they're really interesting to see.
Hey, Space Gamer wants to know what's at the center of M13, and we believe it's a black hole.
Yes, we think there is a black hole at the center of many of these globular star clusters, and not a small black hole either. It's what we call an intermediate mass black hole. So several hundred times the mass of our sun, possibly more than 1,000 times the mass of our sun. Of course, there's also a very massive black hole at the center of the Milky Way galaxy. It has 4 million times the mass of our sun. All right, well, I think we're kind of coming up to the end of our hour here. We'll kind of take whatever questions people want to shoot at us here for the next few minutes.
Some want to know when we're coming back and doing this again.
Yeah, well, that's a good question.
Don't know the answer to that.
We're getting our arms twisted by a lot of people to come back and do this again. We did this every week during the pandemic. It was a lot of fun. That's when Chabot was closed. So we couldn't invite people to come up and look through our telescopes. We couldn't invite you to come up and look at our museum. But once we reopened for after the pandemic sort of wound down, and we restarted our public viewing, we thought, well, there's really no need to do this anymore. But we still get a lot of requests. So I think from time to time we're still going to do this, and let folks watch. One of the things we've noticed is we get a lot of donations this way, but also we get a lot of participation. I can't pronounce it right. Participation from people who could not otherwise come up to Chabot. So we see a lot of people from all over the country and sometimes all over the world tuning into our program. So I think that periodically we're going to continue to do this. So keep your eye out on Chabot's website and Facebook page and YouTube page, and I think you'll see us again not too far in the future.
Hey, we have time for one last quick question.
Yeah.
Sure.
What's the difference between a moon and a moonlet?
Well, it's a kind of a fuzzy boundary. Moons are a little bit bigger. Moonlets are really small. So one of the things that they ran into when they started putting spacecraft into orbit around other planets, especially the gas giants, is the closer you got to the planet, the more you saw smaller and smaller moons. And the question became, when do we stop calling them moons? And the arbitrary limit that has sort of been set now is if it's smaller than 1 kilometer, it's not a moon, it's just a big rock. But I think the moonlet term, we're sort of using that for things that are somewhere in the 10 to 100 kilometer range. Anything bigger than that is a moon, but don't quote me on that. So maybe we can get a Saturn expert here, Carolyn Porco or somebody like that, to come up and give us a better definition. But I don't think there is a precise definition. But think of moonlets as just being really small moons. All right. Any other questions?
We had one person ask, we get this question a lot. What's a good telescope for a beginner? And it's a good question. And my answer is always a good pair of binoculars. A good pair of binoculars.
Binoculars.
Yeah. You'd be amazed what you could see with binoculars. You could see the moons of Jupiter, and you could see that Mars is a red ball. You could see some nebula, and even very bright galaxies.
Even a bit of Saturn's rings could be seen with a good pair of telescopes.
Certainly the moons of Jupiter and so on. Right. But if you want to graduate up from the binoculars, one telescope that we like to recommend is called a Dobsonian telescope. It's a very easy telescope to operate. And they generally have pretty good optics, and you can see a lot more fainter objects out there in space with a Dobsonian telescope. They come in different sizes. I would recommend either a 6 or an 8-inch Dobsonian. They're very simple to operate. They're not in any way motorized or computerized or anything like that. So one downside to them is as the Earth rotates, the object you're looking at will move across the field of view. And so what you have to do is manually keep nudging the telescope to keep the object centered. But that turns out not to be that much of a hassle. Yep. And it's a great way to learn your way around the sky and learn all the objects that are up there, be able to see all the stuff that we're talking about and not spend a whole lot of money doing it.
It's the best bang for the buck.
Yeah.
And one thing to point out is that we have free public observing, as we've said, every Friday and Saturday night from 7:30 to about 10:30. So we have 3 telescopes that are fixed that you all heard about the 8-inch refractor, a 20-inch refractor, and a 36-inch reflector. But we also have generally Dobsonian telescopes, one or more, out on the deck that you can actually take a look at and look through the eyepiece while you're here. So the telescopes that Gerald mentioned, we oftentimes have outside on the deck, and they're open to anyone who is visiting.
Yeah, great opportunity to see what they look like and get a sense of, how they're operated and everything. And, talk to somebody who knows a lot about them and can give you some suggestions on where to get them and things you need to consider in buying them. All right. I think we're about done.
All right.
You're right.
Okay, well, thanks again for joining us, folks. If you haven't done so already, we do ask that you consider making a donation to Chabot Space and Science Center. If you're on Facebook, there's a donate button on the page there. Otherwise, you can go to Chabot's website, which is chabotspace.org. And you'll see a donate button up at the top of the page. You can navigate around, find out about becoming a member and other ways of supporting the Chabot Space and Science Center. We really appreciate your support. That's what helps us do these programs and operate our museum, all our educational programs for local schools. And don't forget also that the Chabot Space and Science Center is now also the NASA Ames Research Center Visitor Center.
Yes.
So we have lots of exhibits up here from the NASA Ames Research Center showing some of the work that they do down there. So come on up and visit us on the weekend.
Yep.
All
right. Nice to see you, everyone.
Yep.
Good night, guys.
Good to see you guys.
Good night.
Good night, everyone.
All right.
Good night.